Okay, so this one I'm looking at test 3, problem 4. So first, if you look at this current carrying loop within an external magnetic field, the magnetic field is actually pointing inward. So I'll just draw an X to symbolize that. So if you look at if you're labeling here, you're supposed to determine what the charge distribution would be on the loop, first of all. And so knowing that there's a force going in to the right, that means there's a velocity to the right. And so if you crossed V inward, you determine that the positive charges will go upward and the negative charges will go downward. So the positive charges travel upward because there's a net magnetic force acting on on negative charges downward. So the distribution would end up like this. And then so knowing this, that conventional current travels from positive to negative, you have this distribution that ends up where the current travels in this direction. It travels clockwise around the loop. And then so if you then from the labeling part, you can determine what the magnetic force is. And so the magnetic force is I crossed with the I crossed with the magnetic field, which is inward, so that ends up going to the left. And so you end up with a magnetic force that travels to the left. And so from the knowing that the loop is traveling at constant speed, you know that the magnetic force and then the force acting on the loop cancel out. And so if you have that to determine the current, you just simply write a sum of forces equations. So the sum of forces on the loop is equal to F minus F the magnetic force is equal to 0. So F is equal to F magnetic. And then since the magnetic force of a current carrying wire is the distance across the short current carrying wire crossed with B, and since the conventional current and the length of the wire and the magnetic field are perpendicular, you know that it's just the magnitudes of the magnetic field and the distance across the wire. So it just ends up becoming B external times H, which H is the height of the wire. And so if you solve for F is equal to, if you solve for I ends up being equal to F divided by B external divided by H. And then so knowing that it's to solve for the velocity, knowing that the electric field is equal to VB because the magnetic force acting on the current carrying loop and the electric force are mutually perpendicular, you can solve for delta V being EL, which is equal to VBH because E is equal to VB. And then knowing that this is the EMF of the current carrying loop, you solve for the current in another manner. I is equal to VB external H over R. And then that is also equal to the predetermined current that's not dependent on velocity, which is F over B external H. You solve for V, and that's what it is.